All right, everyone, get ready, because today we're taking a deep dive into, well, kind of the dark side of
Yeah.
C-sharp development. We're going to be talking about anti-patterns.
Yeah, so these are basically coding practices that may seem perfectly fine when you're starting out,
Yeah.
but they can cause you a lot of pain and headaches later on.
Down the line, yeah. It's like building a house on a shaky foundation.
Yeah,
You know, it might look okay at first, but
exactly.
eventually it's going to come crumbling down.
Exactly. And that's why we're here today to kind of explore these dangerous caves of C-sharp development so you can write better code. And we're going to be using how to avoid anti-patterns in C-sharp development as our guide, but we're not going to just, point out the problems. We're going to really try to understand why they're dangerous and what you can do to avoid them.
Yeah, it's not enough to just know that these things exist, right? We have to learn how to actually avoid them.
Exactly.
So where do we even begin with this?
Well, a classic anti-pattern, one that we all know, and some of us love to hate, is the God object anti-pattern.
Okay, so that sounds ominous. I'm picturing some kind of all-powerful code being that's ruling our code base.
Well, yeah, you could think of it that way.
Is that a good thing or a bad thing?
Definitely a bad thing. Imagine you have a single class, right? And this class is trying to do absolutely everything in your application. Managing user accounts, handling database connections, sending emails, you name it. It's all in this one giant blob of code.
So it's like one person trying to do every job in a company.
Exactly.
That would be chaos.
Absolute chaos. And that's exactly what happens in your code base as well. And one of the core principles that this violates is the single responsibility principle.
Okay, so what exactly is the single responsibility principle?
So SRP essentially states that a class should have one and only one reason to change. So if you have a class that's doing too many things, it's constantly changing, and that makes it incredibly difficult to maintain and to debug.
So it's like if that one person in the company who's trying to do everything, they're going to be constantly bombarded with requests and changes.
Right,
And
exactly.
it's going to be impossible to keep up.
Yeah, and I've personally experienced this, working with God objects.
Oh, really?
Spending weeks tracking down a bug that was caused by a seemingly unrelated change in a massive God object. It's not fun.
Okay, so I'm convinced. No more God objects for me. But how do we actually break down these massive classes into something more manageable?
So one way to think about it is like organizing your workspace. Instead of having one giant cluttered desk, you divide it into different areas for specific tasks, right?
Right.
And in code, we can do the same thing by breaking down our God object into smaller, more focused classes, each with a single responsibility.
Okay, that makes sense. But how do we actually decide how to split things up? Are there any patterns or guidelines we can follow?
Yeah, there are definitely design patterns that can help us with this. Two popular ones are the facade pattern and the strategy pattern.
Okay, I've heard of those, but I'm a little rusty on the details. Can you give me a quick refresher?
Sure. So imagine you go to a restaurant, right?
Okay.
You don't need to know all the intricate details of how the food is prepared. You just interact with the waiter who takes your order and brings you your food.
Right.
And that's essentially what a facade does. It provides a simplified interface to a complex subsystem. So instead of interacting with a bunch of different classes directly, you interact with the facade, which handles the underlying complexities for you.
That's a great analogy. So it's like the facade is the waiter, and all those other classes are the chefs in the kitchen.
Exactly. And the strategy pattern is like having different cooking methods for a dish. You could grill it, you could bake it, you could fry it. Each cooking method is like a strategy, and you can choose the one that best suits your needs. So in code, you might have different strategies for sorting data, for example, and you can easily swap them out depending on the situation.
Okay, so facade simplifies the interface, and strategy gives us flexibility.
Exactly.
Okay, so we've banished the God object and organized our code into smaller units. What's next on our C# anti-pattern hit list?
Well, let's talk about something that seems harmless enough, but can actually lead to major headaches down the road. Hard coding values directly into your code.
Okay, I'm listening. What do you mean by hard coding values? Give me an example.
Sure. Imagine you have your Wi-Fi password, right, embedded directly into your code.
Oh no, I've actually done that before.
And then you need to change your Wi-Fi password. Now you have to go hunt it down everywhere in your code and update it.
Ugh, that's pain. And I'm guessing it's even worse if you're working on a larger project with API keys and database connection strings and stuff like that.
Absolutely. It becomes a maintenance nightmare. And it also makes your application inflexible and difficult to deploy to different environments.
Right, because those values might be different in a test environment versus a production environment, for example.
Exactly.
So what's the solution? How do we avoid this hard coding trap?
The solution is to store these values externally in configuration files. Think of it like having a settings panel for your application where you can tweak these values without having to touch the code itself.
Okay, that makes sense. So we're essentially separating the data from the code.
Exactly.
Okay. And the source material mentions something called dependency injection, or DI. How does that fit into all of this?
So dependency injection takes this concept a step further. Instead of your code directly accessing the configuration file, you inject those configuration values into the classes that need them.
Hold on. I'm sensing this is where things might get a little complicated. Can we break down how DI actually works in practice?
Absolutely. Let's say you have a class that's responsible for sending email notifications, right? Instead of hard coding the email server address and credentials directly into the class, you would define an interface. Let's call it iEmailConfig. And this interface would have properties for, the server address, the port, the credentials, and so on.
Okay, so it's like a blueprint for how to configure email settings.
Exactly. And then your email notification class would receive an instance of this iEmailConfig interface through its constructor.
Okay, I'm following so far. But how does the class actually get that iEmailConfig instance?
Right.
Do we just create one manually whenever we need to send an email?
That's where the injection part comes in. You use a dependency injection container, which is basically a framework that manages the creation and injection of these dependencies.
So the container takes care of creating the iEmailConfig instance, reading the values from the configuration file, and then providing it to the email notification class.
Precisely.
It's like a delivery service that brings the configuration to your code.
Exactly. And the beauty of this approach is that it makes your code much more flexible and testable. You can easily swap out different implementations of iEmailConfig, say, for test purposes, without modifying the email notification class itself.
Okay, I'm starting to see the power of DI. So we're not just keeping our code clean and organized, we're also making it more adaptable and testable. But doesn't DI add a lot of complexity? I mean, when is it too much?
Yeah, that's a valid concern. DI can definitely add a layer of complexity, especially if you're not familiar with it. The key is to find a balance. Don't use it for absolutely everything.
Right.
Use it strategically in areas where it provides the most benefit, like handling configuration values or decoupling components.
So it's a tool in our toolbox, not something we need to use for every single scenario.
Exactly. As you gain more experience with C# development, you'll develop a better intuition for when DI is the right solution and when it might be overkill.
Okay, I'm feeling good about banishing hard-coded values and embracing the power of configuration files in DI. What's next on our C# anti-pattern adventure?
Well, let's shift gears a bit and talk about something that's all about relationships, tightly coupled code.
Okay, are we talking about code getting into, like, unhealthy relationships?
Well, kind of. Imagine you're working on a car,
Right.
but the engine is welded directly to the chassis. Now, if something goes wrong with the engine, you have to replace the entire car.
Yeah, that sounds like a disaster.
And that's exactly what tightly coupled code is like. It's rigid, inflexible, and makes changes incredibly difficult.
I'm sensing a theme here.
Yeah.
Inflexible, difficult to change. These are not words we like to hear when we're talking about code.
Exactly. And this is where the dependency inversion principle, or DIP, comes into play. It's another one of those core principles of good object-oriented design. And it essentially states that high-level modules should not depend on low-level modules. Both should depend on abstractions.
Okay, that sounds very abstract. Can you break it down for me? What does it actually mean in terms of writing C# code?
Sure, let's say you have a class that's responsible for processing orders. And this class needs to interact with a payment gateway to process payments. In a tightly coupled scenario, your order processor class would directly reference a specific payment gateway, like PayPal Payment Gateway.
Okay, so if we ever need to switch to a different payment gateway, we'd have to go into the order processor class and modify it.
Exactly. And that can introduce bugs and break existing functionality. The DIP encourages us to introduce an abstraction, an interface. Let's call it iPayment Gateway.
Okay.
But the order processor and the concrete payment gateways, like PayPal Payment Gateway and Stripe Payment Gateway, would depend on this interface.
So instead of depending on concrete classes, we're depending on abstractions.
Exactly.
These interfaces that define the contract for how those classes should behave.
You got it. And this decoupling gives you incredible flexibility. You can easily swap out different payment gateways just by injecting a different concrete implementation of iPayment Gateway into the order processor class.
Ah, so dependency injection comes into play again. It's not just about configuration, it's also a powerful tool for decoupling components and making our code more adaptable.
You're absolutely right. By embracing the DIP and using DI to manage those dependencies, you create a more modular and maintainable code base that's easier to change and extend.
Okay, I'm convinced. Tight coupling is out and loose coupling is in. What other C-sharp anti-patterns are lurking in the shadows, waiting to trip us up?
Let's talk about something that might seem tempting at first, but can actually lead to code that's rigid and difficult to test. The overuse of static classes.
Okay, I get that. Static classes, they're easy to access from anywhere in your code.
Yeah.
But what's the downside? Why should we be wary of overusing them?
Well, think of it this way. A static class is like that friend who never wants to change plans no matter what.
Okay, I know that friend.
They're set in their ways, and it's just difficult to adapt to new situations.
Right. But why are static classes so inflexible?
One major issue is that they introduce a form of global state into your application. Because there's only one instance of a static class, any changes you make to it are reflected everywhere. And this can make testing incredibly difficult because you can't isolate the behavior of individual components.
So it's like having a single shared whiteboard that everyone's writing on at the same time.
Exactly.
It's hard to keep track of what's going on.
Exactly. And let's say you have a static class called logger that provides logging functionality. Because it's static, you can access it from anywhere in your code, right?
Right.
But when you're testing a specific component, you might not want those log messages to actually be written to a file or a database.
Yeah, that makes sense.
But because the logger is static, it's really difficult to control its behavior during testing.
So how do we escape from this static prison? How do we make our code more flexible?
Well, you guessed it. Dependency injection to the rescue once again.
Of course.
Instead of using a static logger class, you create an interface, like iLogger, and inject a concrete implementation into the classes that need logging functionality.
Ah, so we're back to using interfaces and dependency injection to decouple our components. It's like a recurring theme in our quest to avoid anti-patterns.
It is. It is. It's a very powerful technique. And during testing, you can then inject a mock iLogger that doesn't actually perform any logging. So it gives you much more control over your testing environment.
I'm starting to see a pattern here. Dependency injection, it's like the Swiss Army knife of C-sharp development.
It kind of is.
It helps us with configuration, decoupling, testing, and probably a whole lot more.
Exactly.
Okay, I'm convinced. No more overusing static classes. What else should we be on the lookout for?
Let's talk about something that can really come back to haunt you if you're not careful ignoring exception handling.
Uh-oh, that sounds scary. What are the dangers of not handling exceptions properly?
Well, imagine this. You have a small fire in your kitchen,
Okay.
but you decide to ignore it.
Bad idea.
What happens? It quickly spreads and turns into a raging inferno.
Yeah, definitely a bad idea.
That's kind of what can happen with unhandled exceptions in your code. A small problem can quickly escalate and bring your entire application crashing down.
So it's like ignoring a smoke alarm. We need to be proactive and deal with those exceptions before they turn into major problems.
Exactly. And exception handling is not just about preventing crashes, it's also about building more robust and user-friendly applications.
Okay, so how do we do that? How do we handle exceptions properly?
The key is to implement robust exception handling throughout your code. And this means catching specific exceptions that you anticipate and know how to handle. For example, if you're reading from a file, you might catch file not found exception or IO exception specifically.
Right, so no more generic catch-all blocks.
Exactly.
You need to be specific and intentional about the exceptions we're catching.
Exactly. And then for those unexpected exceptions, the ones you don't anticipate, you can use global exception handling.
Ah, so there's like a safety net for those unexpected events.
Exactly. And logging is another crucial aspect of exception handling. When an exception occurs, you want to capture as much information as possible to help you understand what went wrong and how to fix it.
So instead of just swallowing those exceptions or displaying generic error messages, we should be logging the details for future analysis.
Exactly. Logging frameworks like Serilog or Nlog allow you to capture detailed information about exceptions, including stack traces, timestamps, and contextual data. This information can be invaluable for debugging and troubleshooting.
So we're catching specific exceptions, using global error handling, and logging all the juicy details. This sounds like a solid strategy for building resilient applications.
Absolutely. Ready to tackle another C-sharp anti-pattern?
Bring it on.
Let's talk about a trap that many developers, especially those who are, really passionate about performance, fall into: premature optimization.
Oh yeah, I've definitely been guilty of this. You get so focused on making your code super efficient that you end up overcomplicating things.
Exactly. It's like buying all the fancy race car parts
Yeah.
before you even know how to drive.
Right. You need to learn the basics first.
Exactly.
So what's the smarter approach? Should we just ignore performance altogether?
Of course not. Performance is important, but it's essential to find the right balance.
Okay.
Focus on writing clean, readable, and maintainable code first. Once you have a working solution, then you can start thinking about optimization.
Okay. So we build a solid foundation first, and then we fine-tune the engine.
Precisely.
But how do we know where to focus our optimization efforts? Do we just randomly start tweaking things until we see an improvement?
That's where profiling tools come in.
Yep.
Tools like .trace or Visual Studio Profiler can analyze your code's performance and identify the true bottlenecks.
So it's like having an X-ray vision for your code.
Exactly. They can pinpoint the areas that are actually slowing down your application.
So we profile first, then optimize. Got it. What else should we be aware of on our C-sharp anti-pattern adventure?
Well, let's talk about something that seems harmless enough, but can actually lead to a lot of code bloat and maintainability issues: copy-pasting code.
Oh yeah, I've definitely done that. You're working on a deadline, and you need to implement something similar to what you've done before.
Yeah.
So you just copy and paste a few lines of code, make a few tweaks, and move on.
Exactly. And while it might seem efficient in the short term, it actually violates a very important principle in software development: the DRY principle.
Okay, the DRY principle.
DRY stands for don't repeat yourself.
Okay. So copy-pasting code is essentially repeating ourselves.
Exactly. And when you have the same logic scattered throughout your code base, it becomes really difficult to maintain and update.
Right, because if you find a bug in that duplicated code, you have to fix it in every single instance.
It is exact.
Okay, no more copy-pasting for me. But how do we embrace this DRY principle and keep our code concise and maintainable?
The answer is refactoring.
Refactor.
Regularly review your code base for duplicated logic and extract it into reusable methods, classes, or even separate libraries.
So it's like organizing your tools in a workshop. Instead of having duplicate tools scattered everywhere, you have a designated place for each tool, making it easier to find and use them.
Exactly.
Okay, I like that analogy. So less duplication, more organization.
Exactly. And just like organizing your tools makes you more efficient in the workshop, refactoring your code makes you a more efficient developer.
All right, I'm sold on refactoring. What other C-sharp anti-patterns are we going to uncover on our deep dive?
Well, let's dive into a topic that can be a bit tricky to master: misusing threads.
Okay, this sounds interesting.
Yeah.
They're all about concurrency, right?
Exactly.
Making our applications faster and more responsive.
Exactly. But imagine you have a kitchen where everyone's trying to use the same knife at the same time.
Oh, that's a recipe for disaster.
It is.
Someone's going to lose a finger.
And that's kind of what can happen with threads if you're not careful.
Okay, so how do we avoid turning our code into a chaotic kitchen? How do we manage threads effectively?
Well, first and foremost, embrace asynchronous programming techniques. The asyncoate keywords in C# provide a very powerful and relatively straightforward way to write asynchronous code without getting bogged down in the complexities of manual thread management.
Okay, so async await helps us manage those threads without pulling our hair out.
Exactly. And for situations where you need true parallelism, you can leverage parallel libraries like the task parallel library, or TPL, or parallel LINQ, PLINQ. These libraries provide higher level abstractions for working with threads.
Okay, so async await for asynchronous operations and parallel libraries for true parallelism. Got it. But there's still the issue of synchronization, right? We don't want our threads tripping over each other and creating havoc.
You're absolutely right. Understanding thread synchronization mechanisms like locks, mutexes, and semaphores is crucial to prevent race conditions and deadlocks. These tools help coordinate access to shared resources.
So they're like traffic signals for our threads, making sure everything flows smoothly and safely.
Exactly. And careful thread management is essential for creating robust and reliable applications.
All right, noted. What's next on our anti-pattern exploration?
Let's talk about something that's often neglected but can have disastrous consequences: neglecting unit tests.
Uh-oh. I know testing is important, but sometimes it feels like an extra step that slows down development. Why is it so crucial to write unit tests?
Well, imagine you're building a house, but you decide to skip the foundation inspection.
That's a bad idea.
It is. What could happen? The house could collapse. And that's kind of what can happen with untested code. Hidden bugs can lurk in the shadows, waiting to strike and cause problems.
So unit tests are like our foundation inspection, making sure our code is solid and stable.
Precisely.
Okay, I'm convinced. Testing is crucial. But what are some practical tips for writing effective unit tests?
Well, one important principle is to keep your unit tests focused. Each test should verify a single, specific aspect of your code's behavior.
Okay, so no more mega tests that try to do too much.
Exactly.
We need to break things down into smaller, more manageable units.
Exactly.
Makes sense.
Yeah.
And we talked about mocking libraries earlier. How do those fit into unit testing?
Mocking libraries are incredibly useful when writing unit tests because they allow you to isolate the component that you're testing.
Okay,
You can create fake versions of dependencies
right.
so that your tests focus solely on the behavior of the unit under test.
So it's like creating a controlled environment for our tests, where we can manipulate the inputs and outputs and make sure our code is behaving as expected.
Exactly.
Okay, so we're writing focused unit tests using mocking libraries to isolate components and building a solid foundation for our code. What other anti-patterns are lurking out there?
Well, let's wrap up this first part of our deep dive with an anti-pattern that often stems from good intentions, but can actually lead to unnecessary complexity over engineering.
Oh yeah, I've definitely been guilty of this. You start thinking about all the potential future scenarios, and you end up building this really complicated system that's way more than you actually need.
Exactly. It's like buying a giant SUV when all you need is to drive to the grocery store.
Right, sometimes a bicycle will do the job just fine.
Exactly. And that's where the YIGNI principle comes in.
Okay, the YIGNI principle, what's that?
YIGNI stands for you ain't gonna need it.
Haha, I like that. Straight to the point.
And it's a powerful reminder to focus on solving the problems at hand, not hypothetical problems that might never arise.
Okay, so start simple, focus on the current needs, and refactor as your requirements evolve.
Exactly. Over-engineering leads to code that's harder to understand, maintain, and extend. It's like building a Rube Goldberg machine to simply turn on a light switch.
Okay, I'm definitely on board with the YIGNI principle. But how do we prevent ourselves from going overboard? How do we keep our designs aligned with actual needs?
Regular design reviews are essential. By involving other developers and stakeholders in the design process, you can get valuable feedback and make sure you're not over-engineering.
So we're starting simple, refactoring as needed, and using design reviews to keep things on track. That sounds like a great set of strategies for avoiding over-engineering. Wow, we've covered a lot of ground in this first part of our deep dive into C-sharp anti-patterns.
We have, but we've only just scratched the surface.
Oh, there's more.
There's always more to explore. In part 2, we'll continue our journey, diving deeper into these anti-patterns and exploring practical examples to help you solidify your understanding.
Okay, I'm excited for part 2. This is like a C-sharp thriller, keeping us on the edge of our seats, waiting to see what happens next.
I like that analogy.
Until next time, folks, keep those coding skills sharp.
And stay tuned for more C-sharp anti-pattern adventures.
All right, welcome back to our deep dive into C-sharp anti-patterns. Last time we were mapping out some pretty dangerous territory, God objects and hard-coded values and all that stuff.
Right, exactly. But remember, we don't just want to identify these hazards. We want to figure out how to navigate them effectively.
Yeah, exactly. It's not enough to just know they're out there. We got to learn how to actually avoid them.
Exactly. So let's revisit some of those anti-patterns we talked about, dig a little deeper, and maybe look at some practical scenarios, to make sure we really understand the why.
Okay, sounds good to me. So where should we start our descent?
Let's start by revisiting the God object. Remember our analogy? The one person trying to handle every role in the company.
Yeah, I remember. One person doing everything. It's a recipe for burnout in the real world, and in code, it's just a tangled mess.
Exactly. But how does this actually play out, in a real coding scenario?
Yeah, give me an example. Like, how would this manifest, in a real project?
Imagine you're building an e-commerce application, and you have this class called, let's say, User Account Manager. And it's handling everything related to user accounts. So registration, login, password management, order history, wish lists, you name it.
Whoa, hold on. That's a lot of responsibility for just one class to handle. I
Exactly.
can see how that would quickly become, this massive, unmanageable monster.
Exactly. And this class, I mean, it would have hundreds, maybe even thousands of lines of code.
Wow, yeah.
Really difficult to understand, and even like a small change could, have these unintended consequences.
So, like, if you're trying to fix a bug in one part of the class,
Yeah.
you might accidentally break something completely unrelated.
Exactly. It's like a house of cards. You touch one thing and the whole thing could come tumbling down.
Okay, yeah, I'm definitely seeing the problem here. So how do we actually refactor this behemoth into something that's, more manageable? How do we apply that single responsibility principle we talked about last time?
Remember our workspace analogy. Instead of having that one giant desk, we divide it up into smaller
Right,
areas.
right.
And in code, we can do the same thing by breaking down our giant user account manager into, smaller classes.
Okay, so we might have like a separate class for user registration, a separate class for password management, and
Yeah,
so on.
exactly. So you might have a user registration service, a password manager, an order history service, and so on.
Okay, so each class is handling, just one specific aspect of user account management.
Exactly.
Okay, that makes a lot more sense. So what's another anti-pattern we should take a closer look at?
Let's revisit hard coding values. Uh, Remember that Wi-Fi password example from last time?
Yeah. Embedding your Wi-Fi password directly into your code, not a good idea.
Not a good idea. Now imagine that scenario, but on a larger scale, right? Hard coding API keys,
Yeah.
database connection strings, file paths, all those, crucial bits of information.
Right, yeah.
And then, what happens if those values need to change?
Yeah, you have to go hunting through your code and update them everywhere.
Exactly. And it's not just about the hassle of updating them. Okay. It also makes your application less portable.
What do you mean by less portable?
Well, what if you need to deploy your application to, let's say, a different environment, right? A test environment or a staging environment.
Right, yeah. Those values might be different.
Exactly.
Okay, yeah, I see the problem. So we store those values in external configuration files instead.
Yeah.
But couldn't someone just open up those configuration files and see all those sensitive values?
That's a great point. And that's why security is definitely a concern. And, configuration files should never store highly sensitive information like passwords or API keys in plain text.
Okay, so how do we protect those sensitive values?
Well, there are, several approaches you can take. One option is to encrypt those values.
Okay.
Another approach is to use environment variables.
Okay.
Or you can use secrets management tools.
Okay, so we're taking steps to, protect those sensitive values and make sure that unauthorized people can't access them. Makes sense. We talked about dependency injection as a way to access those configuration values. Can you give me an example of how that would work in practice?
Absolutely. Imagine you have a class, and this class needs to connect to a database. So instead of hard coding the connection string directly into the class, you would define an interface. Let's call it iDatabase config.
Okay.
And this interface would have a property for the connection string.
Okay, so something like this.
Yeah.
Like public interface, iDatabase config, and then we have a property for connection string.
Exactly. And then your class that needs to connect to the database would receive an instance of this iDatabase config interface through its constructor.
Okay, so the dependency injection container would take care of, reading that connection string from the configuration file and providing it to our class. So it's kind of like a middleman, fetching the data and delivering it where it needs to go.
Exactly. And the beauty of this is that your class doesn't actually need to know where the connection string is coming from. It's simply provided to it.
Okay, yeah, that makes sense. So dependency injection and configuration files, they're working together to make our applications more flexible and adaptable.
Exactly.
Okay, so what other anti-patterns should we delve into?
Let's revisit tightly coupled code. Remember our car analogy?
Oh, yeah. You have to
Yeah.
weld it to the chassis.
Yeah.
I'm starting to think you have a thing for cars.
Maybe. But yeah, remember that analogy. Tight coupling, it makes our code rigid and difficult to change. Now imagine you're building a reporting feature for your application, right?
Okay.
And you have this class called report generator. And it's responsible for, generating these reports.
Right.
Now, in a tightly coupled scenario, your report generator might directly reference a specific data access class, let's say still data access, to retrieve the data for the report.
Okay, so the report generator is directly tied to that specific way of accessing data.
Exactly.
So if we ever need to change how we access data, like switch to a different database or use a web service or something,
Then you have to go into the report generator and modify it.
okay, and that can introduce bugs and all sorts of problems.
Exactly. It also makes it difficult to reuse the report generator in other parts of your application.
Right, yeah, because it's so tightly coupled to that specific data access method.
Exactly.
Okay, I'm seeing the problem. So how do we, uh, how do we avoid this tight coupling? How does the dependency inversion principle come into play here?
Remember, the DIP tells us to depend on abstractions, not on concrete implementations. So instead of referencing that SQL data access directly, we introduce an interface. Let's call it iData access.
Okay, so it's like we're creating a contract that specifies how different data access methods should behave.
Exactly. And both the report generator and the, concrete data access classes like SQL data access, web service data access, they would all depend on this iData access interface.
Okay, so the report generator doesn't care which specific implementation it's using as long as it follows the rules of the contract, right?
Exactly.
That makes sense. And of course, dependency injection comes into play again here, right?
Exactly. Your DI container takes care of providing the appropriate iData access implementation to the report generator.
So we're using dependency injection and the dependency inversion principle to create, this loosely coupled system.
Exactly. And this makes your code much more flexible, adaptable, and maintainable in the long run.
Okay, I'm definitely getting the message here.
Okay.
Decoupling is good. So what else should we examine under our C# anti-pattern microscope?
Let's revisit the overuse of static classes. We talked about how static classes introduce this, form of global state.
Right,
And they
right.
make it difficult to isolate components during testing. So can we see a practical example of this testing challenge?
Yeah, I'd like to see how this plays out, in a real testing scenario.
Yeah. Absolutely. Imagine you have a class called user controller that handles user registration. And this user controller uses a static email service class to send welcome emails to new users.
Okay, so we have something like this. Public class user controller, and then a method called like register user, and then inside that method we're calling email service send welcome email.
Exactly. Now imagine you're writing unit tests for this user controller, right?
Okay.
You want to make sure that the register user method is doing everything correctly. It registers the user, it sends the email, all that good stuff.
Right, but we don't want to be sending actual emails during our tests.
Exactly. That would have unintended consequences.
Right.
It would also slow down your tests.
Yeah, that makes sense.
But because email service is static, it's really difficult to control its behavior during testing.
So our tests are not really isolated anymore. They're actually interacting with, external systems.
Exactly. And that's one of the major downsides of overusing static classes.
Okay, so how do we avoid this testing pitfall?
You guessed it. Dependency injection.
Of course. Our trusty friend, dependency injection.
Exactly. Instead of using a static email service, we create an interface, like iEmail service, and inject a concrete implementation into the user controller.
Okay, so we're essentially decoupling the user controller from the concrete email service implementation.
Exactly. And during testing, you can inject a mock iMail service that doesn't actually send real email. So it gives you much more control over your testing environment.
Okay, so dependency injection, it's not just about configuration or decoupling. It also helps us with testing. This is really powerful stuff. But I'm curious, are there ever situations where static classes are actually a good fit?
Oh, absolutely. If you have, let's say, utility functions that don't depend on any external state or have any side effects, then using a static class can be a perfectly valid choice.
Okay, so it's not about completely avoiding static classes. It's about, using them judiciously and understanding their limitations.
Exactly.
Okay, makes sense. So what's the next anti-pattern on our list?
Let's revisit ignoring exception handling. Remember that small fire in the kitchen?
Yeah. Yeah, definitely don't want to ignore that.
Well, exception handling is kind of similar. We need to make sure that we're handling those exceptions properly. And one of the key aspects of exception handling is logging.
Okay, so instead of just like swallowing those exceptions or displaying, generic error messages, we should be logging the details so we can, you know, analyze them later.
Exactly. Logging frameworks like Serlog or Nlog can capture detailed information about exceptions, including stack traces, timestamps, all that good stuff.
So it's like a breadcrumb trail.
Right.
It
Exactly.
helps us figure out, what went wrong and how to fix it.
Exactly.
Okay, so we're logging the exceptions, but what about the user experience?
That's a great point. You don't want to bombard the user with technical jargon and error messages.
Right, yeah. No one wants to see a wall of text filled with stack traces and all that stuff.
Exactly.
So what should we do instead?
Well, strive to provide user-friendly error messages that explain the problem in plain language, and maybe even offer some suggestions for resolving the issue.
Okay, so we're not just, handling the exception from a technical perspective. We're also thinking about, impact on the user
Exactly.
and making sure that they have a smooth experience
Yeah.
even when things go wrong.
Exactly.
Okay, that makes sense. So what's next?
Let's revisit premature optimization. Remember buying all those fancy race car parts before you even know how to drive?
Yeah, don't get ahead of yourself.
Exactly. But how do we actually know, where to focus our optimization efforts?
Yeah, how do we know what to optimize?
That's where profiling tools come in handy. Tools like Dot Trace or Visual Studio Profiler can analyze your code and tell you exactly, what's slowing down your application.
So it's like having a detective for your code. They can help you uncover those hidden culprits that are dragging down the performance.
Exactly. And profiling helps you separate fact from fiction. Instead of just guessing, you're actually using real data to guide your optimization efforts.
Right. So we're not just throwing darts in the dark. We're actually, aiming for a specific target. We're using data to guide our decisions. So we've written our code, we've profiled it, we've identified the bottlenecks. Now we're ready to optimize. But what are some general strategies we can use to make our code run faster?
Well, there are countless optimization techniques, but some common ones include caching, algorithm optimization, database optimization, asynchronous operations, and so on.
So it's not just about, making one specific change. It's about taking a holistic approach and looking for opportunities to, improve efficiency at different levels of the application.
Exactly. And optimization is an ongoing process. It's not something you just do once and forget about it.
Right.
You need to constantly monitor your application's performance and look for ways to improve it.
Okay, so optimization is a journey, not a destination. Got it. So what's next on our anti-pattern hit list?
Let's revisit copy pasting code. We talked about the DRY principle last time. But sometimes it can be really tempting to, copy and paste a few lines of code instead of creating, reusable components.
Yeah. It seems easier in the moment,
Mm.
but we know that it can lead to, code bloat and maintenance headaches down the road.
Yeah.
But sometimes those few lines of code are so specific to, that particular scenario. It almost seems like overkill to, create a whole separate method or class for them.
Right. And it's definitely a judgment call. There's no hard and fast rule. But here's a general guideline. If you find yourself copy pasting the same block of code more than, let's say, twice,
Okay.
it's probably a good sign that you should be refactoring.
Okay, so it's not about, avoiding duplication at all costs. It's about, recognizing patterns and finding opportunities to, make our code more concise and maintainable.
Exactly.
Can we see an example of, how refactoring can help us eliminate this code duplication?
Absolutely. Imagine you're building a web application and you have several forms that require, input validation. You might be tempted to copy paste the validation logic for each form.
Oh, yeah, I've definitely done that before.
Yeah.
You're on a roll, you've got the validation logic working for one form, and then you need to do something similar for another form, so you just copy paste, make a few tweaks, and move on. But I'm guessing that's not the best approach.
Right. And while it might seem efficient in the short term, it creates a lot of redundancy. And what if, later on you discover a bug in your validation
Oh,
logic?
yeah, you have to fix it in, multiple
Oh,
places.
exactly.
Okay, yeah, I see the problem. So how do we refactor this into something more reusable?
Well, you could create a separate class, let's call it input validator, with methods for common validation tasks like validating email addresses, phone numbers, passwords, and so on.
Okay, so instead of copy-pasting those validation checks,
Yeah.
each form, we just call the appropriate methods from our input validator class.
Exactly.
Okay, yeah, that makes a lot more sense. It's like having, a validation expert on call, ready to validate any input that we throw at it.
Exactly. And just like having an expert on your team makes things easier, having reusable components in your code base makes development smoother and more efficient.
This has been a really insightful deep dive so far.
Glad to hear it. But we're not done yet.
Oh, there's more.
There's always more to explore.
Okay, keep them coming.
In part 3, we'll continue our journey. We'll be covering more anti-patterns, and we'll dive into some advanced techniques for writing cleaner, more efficient, and more maintainable C# code.
Okay, I'm excited for part 3. This is like a C# mystery novel. We're uncovering clues and solving puzzles along the way.
I like that.
Until next time, folks, keep those coding skills sharp. Welcome back, everyone, to the final part of our deep dive into C# anti-patterns. We've uncovered a lot of treacherous coding practices so far.
Yeah, we've explored some of those shadowy corners of C# development.
Right, those hidden pitfalls that can really trip us up if we're not careful.
Exactly. But remember, the goal isn't just to identify these hazards.
Right.
It's to learn how to navigate them effectively.
Yeah, exactly. We want to emerge from these code caves as stronger, more skilled C# developers.
Exactly. So, are you ready to tackle those final few anti-patterns?
Absolutely. Lead the way.
Okay, let's revisit misusing threads. We talked about async await for those asynchronous operations, and we talked about those parallel libraries for true parallelism.
Right, right.
But there's one more crucial aspect we need to address: thread synchronization.
Yeah, we touched on this briefly in part 2. The analogy of the chefs all trying to use the same knife in the kitchen.
Right,
I
exactly.
have a feeling this is where things can get really tricky if we're not careful.
You're absolutely right. Thread synchronization is where a lot of developers get tripped up. Imagine you have, multiple threads trying to access and modify the same shared resource, like a data structure or a file.
Yeah, so it's like having multiple people trying to edit the same document at the same time, without any version control.
Exactly. And without proper synchronization, you end up with data corruption and race conditions and all sorts of unpredictable behavior.
So it's like a recipe for disaster.
It is. It is. And it can be incredibly difficult to debug those kinds of problems.
Okay, I'm seeing the potential for chaos here.
Yeah.
But how do we prevent these concurrency nightmares? How do we make sure our threads are playing nicely together?
Well, that's where those thread synchronization mechanisms come in. These mechanisms, like locks and mutexes and semaphores, they provide a way to control access to those shared resources and make sure that, only one thread can modify them at a time.
So they're like traffic signals, right?
Yeah.
Directing the flow of traffic and preventing collisions.
Exactly. A great analogy. Each synchronization mechanism has its own, nuances and use cases, but they all serve that same fundamental purpose: to coordinate access and prevent those concurrency issues.
Okay, that makes sense. Can we see an example of how these synchronization mechanisms actually work in practice? I'm having a hard time, picturing how we'd actually implement them.
Absolutely. Let's say you have a multi-threaded application, and in this application you have, multiple threads that need to update a shared counter. So imagine something like this.
Okay, so we have a class called counter, and it has a private field value to store the count, and then a method called increment that, increments the counter.
Exactly. Now imagine multiple threads calling that increment method simultaneously. Without synchronization, you can end up with, an incorrect count.
Right, because one thread might read the value, increment it, and then another thread might come along and read the old value before the first thread has had a chance to, write back the updated value.
Exactly. So we're essentially losing increments because, those threads are stepping on each other's toes.
Okay, yeah, I see the problem. So how do we fix it? How do we prevent those lost increments?
Well, we can use a lock to make sure that, only one thread can access that value field at a time.
Okay, so we wrap that increment logic in a lock statement.
Exactly. So the lock statement ensures that only one thread can acquire the lock at a time. And any other threads trying to, enter that protected section will be blocked until the lock is released.
So it's like having, a bouncer at the door of a nightclub, making sure that, not too many people are trying to get in at the same time.
Exactly. A great analogy. And by using these locks strategically, we can prevent those concurrency nightmares and make sure that our applications are, behaving predictably and reliably.
Okay, this is really helpful. I'm starting to see how important thread synchronization is,
Mm.
especially as we, build these more complex applications. So what other anti-patterns should we address in our final deep dive?
Let's revisit neglecting unit tests. We've talked about the importance of writing those tests, but let's dig a little deeper into some strategies for making those tests, really effective.
I know testing is important, but sometimes it feels like just this extra step that slows down development. Are there ways to make, testing less painful?
Absolutely. And one key strategy is to embrace test-driven development, or TDD.
Okay, I've heard of TDD, but I'm not entirely sure how it works. Can you give me a quick overview?
Sure. So TDD involves writing your tests before you write your code.
Okay.
It might seem counterintuitive, but it really forces you to think about, that desired behavior of your code up front,
Okay.
and it helps you design more testable code.
So instead of writing the code and then trying to figure out how to test it, we're starting with the tests, and those tests are guiding, our development process.
Exactly. The typical TDD cycle involves 3 steps. First, you write a failing test that describes the desired behavior. And then you write the minimal amount of code to make that test pass. And then you refactor the code to, improve its design and maintainability, while, of course, making sure those tests still pass.
So it's like we're setting a target, and then we're aiming for it, right? The
Exactly.
tests are our target, and they're guiding our development process.
Exactly.
Okay, that makes sense. So we're embracing TDD, but how do we actually write those tests? What are some tips for creating, effective and meaningful unit tests?
Well, one important principle is to keep your unit tests focused. Each test should focus on verifying a single specific aspect of your code's behavior.
Okay, so it's back to the idea of breaking things down into smaller, more manageable units, right?
Exactly. Focus tests are easier to understand, easier to maintain, and easier to debug.
Right, right. And we talked about using mocking libraries to isolate the unit under test. Can you remind me why that's so important?
Sure. So mocking libraries let you create these fake versions of your dependencies.
Okay.
This gives you more control over that testing environment and allows you to, really test your code in isolation.
So it's like creating a controlled laboratory environment for our tests.
Exactly. A great way to put it. And it helps you avoid those, it works on my machine scenarios.
Right,
Yeah.
yeah. Where the tests pass locally, but then, they fail in other environments because, those dependencies might be behaving differently.
Exactly. So mocking helps you avoid those situations.
Okay, so we're writing focused unit tests. We're using mocking to isolate components, and we're considering, embracing that TDD approach. Any final thoughts on avoiding anti-patterns and just writing better C# code in general?
Well, avoiding anti-patterns is an ongoing journey. It's about, constantly learning and improving your skills. Be curious, experiment, learn from your mistakes, and be open to, new ideas and techniques.
Yeah, it's like we're craftsmen, right? We're constantly honing our skills and trying to, produce the best possible work.
Exactly.
Well, this has been an incredibly insightful deep dive. I feel like I've learned so much about, not just what anti-patterns are, but how to actually avoid them in my own code.
Well, that's great to hear. I'm glad you found it helpful.
I think anyone listening to this, is going to walk away with some really valuable insights. So thank you for sharing your expertise with us.
Oh, it was my pleasure. Always happy to, help developers write better code.
And to our listeners, thank you for joining us on this C# anti-pattern adventure. We hope you've enjoyed the journey.
And that you'll continue to explore those code caves with confidence and a newfound appreciation for the power of well-written code.
Until next time, happy coding, everyone.